They say that the size doesn't matter, but this is not the case for our first presentation, in which what we are looking for is not big sizes, but small sizes. Carlos Sanchez Somolinos, who's a PhD in physics, and he was a postdoc at the Eindhoven University of Technology in the Netherlands. Then he joined the Institute of Materials Science of Aragon, ICMA, where he's a scientist and vice-director. He leads the Advanced Manufacturing Laboratory. His current interests focus on the development of functional materials and their micro-manufacturing, seeking for functional structures and surfaces of interest in the area of optics, biomedicine, and soft robotics. He's going to present a talk, 4D printed actuators with soft robotic functions.
Thank you very much for the kind introduction. Thank you also to the organizers for giving us the chance to present our work here, our laboratory and our work here. For those not knowing us, at the Advanced Manufacturing Laboratory, through a multidisciplinary approach, we are working on the design and preparation of micro and nanostructure polymeric systems with functionalities of interest in information and communication technologies, biomedical, and soft robotics. We mainly focus, but we are not limited to, functional organic materials, namely photopolymers, liquid crystal materials, functionalized with functional molecules or polymers. And to turn these systems into functional polymeric systems, we need to control their morphology. And for this, we count with a plethora of advanced manufacturing tools. We count with self-assembly, that is for free, but we also count with mask and holographic photolithographies, direct laser writing, and additive manufacturing techniques like inject and 3D printing. We undertake with this different projects, focus on nanolithography, optics and photonics, biomedicine, and soft robotics that I will talk today about it. We work on soft actuators that are polymeric systems that deform in a prescribed fashion, a prescribed shape in response to an external stimuli that can be heat, can be light, can be a magnetic field. These systems are characterized by flexibility and adaptability in the deformation, so they can deform and adapt to delicate and handle delicate objects. So they are interesting, they have a strong potential in the implementation of soft robotic functions with potential use in minimally invasive surgical devices. That is what brings me here today. In this field, the liquid crystalline polymeric networks are of great interest since they show an isotropic deformation when they are exposed to an external stimulus like light or heat. An increment in the disorder of the molecules in the system leads to a contraction of the system along the direction of preferential direction and an expansion in the perpendicular directions. So this is this cartoon is essential to comprehend, to understand what will come later. And as an example of deformation of this type of system, here you have a film in which through the thickness there is a change of orientation through this, from this direction to the perpendicular direction. So an increase of temperature produces a contraction along the direct preferential orientation direction. So we have a contraction in the top part of the film. We have an expansion in the bottom part. So the system accommodates these stresses by bending up, by going out of the plane. And this has been employed by many authors for the preparation of cantilevers, photoactuated cantilevers, artificial cilia for microfluidics, and even walking devices. I approach now to our topic, and I mention here 3D printing, that, as you know, is an additive, consists in the additive digital addition of materials to build complex three-dimensional objects that are of interest, of course, in rapid prototyping, but are also being exploited in the field of medicine. Typically, 3D printed uses thermoplastic materials that, after printing, leads to inanimated three-dimensional objects. The concept of 4D printing, introduced by MIT 4 years ago, goes one step beyond and introduces time, since we are printing materials that respond to an external stimulus. We can print an object, and upon stimulation, the object can evolve on time. In this framework, we have developed a platform of materials and a printer, liquid crystalline materials, that we can print using our printer. We can fix it using a UV light, and we can grow in the set direction. We can build three-dimensional objects, and advantageously for us, we have seen that during printing, the molecules tend to align along the movement direction of the needle. So we are able to have an exquisite control of the morphology of the material, of the printed material. So once fixed, we have this morphology, this orientation of the material. So heating this material will lead a contraction along this direction and expansion along the other direction. So here you have an example of a freestanding fiber that contracts and upon heating, and also expands in the other direction. The additive character of the 3D printing technology allows us to generate thick elements with this material, scaling up the capacity to create work, to generate mechanical work, and creating in this way real artificial muscles that respond to heat, but can also be designed. We can design materials that respond to other stimuli. By controlling the orientation in the plane, the orientation of the molecules in the plane, we can generate more complex deformation patterns, structures. For example, this helical structure evolves with heating to this cone morphology that can be used, potentially be used as a micropump, or we can generate open structures in which here you see a movie of the formation of the cone. Here you see a movie of a membrane that changes the shape and the size of the pores upon heating. We have also generated chiral elements that can rotate objects, generating this robotic function. And we have also integrated these materials in other materials, for example, PDMS, generating what you see here, this lens that responds to temperature. You can see how the paper over there is focused on heating, being all these effects, of course, reversible on cooling. Just to finish, as a conclusion, we have created a 4D printing platform that allows us to digitally program mechanical stresses in the material through the control of the morphology, and allows us to implement complex robotics functions that with potential interest in medical devices. Thank you very much.